Good afternoon, respected chairpersons, conference organizers, reviewers, and fellow researchers. I am architect Karthik Chadalavada, assistant professor from School of Planning and Architecture, Vijayawada. Today, I'll be presenting our research titled A Passive Design Benchmarking Framework for Residential Buildings in Warm and Humid Climatic Zone. Yes. So today, the research focuses on developing a climate responsive passive design assessment framework, especially for warm and humid climatic regions. This study attempts to address the limitations of existing international green building rating systems, which often do not adequately respond to the climatic realities of tropical warm and humid regions. The framework was developed using literature based parameter extraction, expert through Delphi methodology, and statistical validation using PCA and ANOVA. The ultimate aim of this establish measurable and scientifically validated passive design benchmarks for sustainable residential development in warm and humid climatic regions. So coming to the slide 2, which is the abstract. So this study originates from the major gap identified in current green building assessment systems. Most existing rating systems such as LEED, BREEAM, and even many national frameworks are generalized systems developed for multiple climatic contexts. However, warm and humid regions have very unique environmental conditions, high humidity, high solar radiation, limited diurnal temperature variations, and high dependence on mechanical cooling. Because of this, buildings designed using generalized rating systems often perform inefficiently in tropical regions. So, the objective of this research was therefore to develop a climate specific passive design rating system, especially for warm and humid residential buildings. So, to achieve this, a systematic literature review was conducted, passive design indicators were extracted, 3-round Delphi study with 25 experts was performed, and statistical validation using PCA and ANOVA were applied. The results demonstrated strong expert consensus, high statistical reliability, and the development of measurable benchmarking framework. So the proposed framework contributes towards climate responsive housing policy, sustainable residential planning, and passive energy efficient designs. So coming to the next slide, which is the introduction slide. So this slide explains the broader research problem. Global green building systems were primarily developed for temperate climate conditions found in Europe and North America. So as a result, they emphasize on insulation, air tightness, and generalized energy reduction strategies. However, in warm and humid climates, these strategies may not work effectively. For example, excessive insulation can trap humidity, airtight envelopes can increase moisture accumulation, and inadequate ventilation can reduce thermal comfort. So, literature study indicates that more than 80% of passive design studies neglect latent heat and humidity control. This leads to the building that are technically rated as green but are uncomfortably in actual tropical conditions. In cities, the cities in India like Mumbai, Chennai, and even Singapore and coastal tropical regions, this mismatches because which is highly evident. So another important issue is that existing systems do not sufficiently integrate local building traditions, vernacular passive responses, or even occupant adaptive behavior. Therefore, this research proposes a climate specific passive benchmarking framework tailored specifically for warm and humid residential environments. So, coming to the next slide, which is research aim and objectives. This slide presents the overall research structure. The primary research aim was to develop and validate a climate specific passive design rating system for warm and humid residential buildings. Four key research questions guided the study. Which passive design parameters most influence thermal comfort and energy efficiency? Can expert consensus reliability validate these parameters? Can the identified variables be statistically grouped into meaningful dimensions? Does professional background significantly influence the expert opinion? So the research methodology was organized into 5 stages: literature review, Delphi study, PCA, ANOVA, and final PDRS development. So coming to the next slide, that is warm and humid climate. So what defines warm and humid climate? This slide defines the climate context of the study. The research follows the National Building Code of India for climatic classification. So warm and humid climate are characterized by high temperature throughout the year, relative humidity above 70%, strong solar exposure, and limited nighttime cooling. So, under these conditions, occupant typically experience thermal discomfort, PMV values shift towards warm and hot conditions, and even cooling loads increase significantly. The challenges in such climates is not only temperature reduction but also humidity control. Therefore, the passive design strategies must prioritize cross ventilation, shading, moisture control, reflective materials, and adaptive comfort. The target of the passive design is to bring indoor comfort closer to neutral thermal sensation while minimizing mechanical cooling dependency. So coming to the next slide, which is the literature survey. So this slide summarizes findings of systematic literature review. A large number of studies demonstrate that passive design strategies can significantly improve thermal comfort and reduce energy demand. For example, optimized ventilation can improve airflow by more than 60%. Reflective roofs can reduce indoor temperatures, and envelope optimization can substantially lower cooling loads. However, most studies focus on isolated strategies. Very few studies integrate these strategies into comprehensive assessment frameworks. And another major issue that was identified from many simulation based studies failed to account for occupant behavior, humidity variation, and urban heat island effects and cultural adaptability also. Therefore, the literature study clearly indicates the need for unified expert validated benchmarking framework, especially for warm and humid residential buildings. So coming to the next slide, which is the research gap. So this slide explains the identified research gap. Currently, architects, engineers, policymakers, and even the planners are being there. So do not have reliable climate-specific assessment framework for passive design in warm and humid regions. Most existing systems are either over-generalized, simulation-dependent, or focused on individual strategies only. The research gap analyzed identified five major limitations, that is lack of integrated frameworks, limited humidity, over dependency on simulations, weak contextual adoption, and not validated passive benchmarking tool. So this research attempts to bridge these gaps by developing a multidimensional framework integrating passive performance, climate suitability, and measurable benchmarks. So coming to the next slide, which is research methodology. This slide explains the overall research methodology. The methodology was divided into three phases. The phase one, which is literature review, variable extraction, and development of preliminary framework. Coming to the phase two, which is a three-round Delphi study, expert evaluation, and consensus development. The expert panel includes architects, civil engineers, energy analysts, and sustainable consultants. Coming to the phase three, which is statistical validation, dimensional reduction through principal component analysis, and agreement testing using ANOVA tool. This mixed method approach ensures that the framework is technically valid, statistically reliable, and contextually appropriate. So coming to the core indicators that are derived from the literature. So from the literature review, 42 passive variable designs were initially identified. However, not all variables were equally relevant to the warm and humid climates. Therefore, a three-stage filtering process was applied, which is frequency in literature, measurability, and humidity relevance. Finally, five core indicators were derived, which is building layout and geometry, fenestrations, walls, roofs, infiltration, and air tightness. So these indicators directly influence thermal comfort, ventilation performance, gain, moisture behavior, and energy efficiency. The framework ensures that all the selected indicators are measurable and scientifically quantifiable. So coming to the next slide, which is the first one, that is Delphi method. So this slide explains the Delphi methodology used for expert consensus. The Delphi method was selected because it enables structured and iterative expert evaluation. The process involves three rounds. Round one, which is qualitative feedback, round two, which is quantitative rating, and round three, which is consensus finalization. So experts evaluated parameters based on importance, feasibility, and climate suitability. So across the rounds, redundant variables were being removed, overall indicators were being refined, and consensus progressively improved. So finally, 21 validated parameters were retained from this particular framework. So coming to the Delphi results that we have it. So this slide presents the statistical reliability of Delphi process. Kendall coefficient of concordance increased from 0.68 in round 1 to 0.89 in round 3. This indicates very strong consensus among the experts. Reliability testing using Chronobox Alpha provided a value of 0.952, which indicates excellent internal consistency. This means the framework is highly reliable and expert responses are statistically stable. Therefore, the retained parameters can be considered scientifically validated from warm and humid passive design assessment. So coming to the next slide, which is PCA and ANOVA, which is principal component analysis and ANOVA. So to further validate the framework, PCA and ANOVA were conducted. So PCA was used for dimensionality reduction and identification of latent relationships among the variables. The analysis extracted two principal components explaining 85.23% of total variance. This indicates that the framework effectively captures the majority of passive design performance characteristics. Coming to the ANOVA, which is a testing professional group bias. So the results showed that although minor differences existed, there was no major contradiction among the expert groups. This confirms that the framework is multidisciplinary, relevance, and broad professional applicability also. Coming to the next slide, which is correlation matrix. So this slide illustrates the relationship among passive design variables. The correlation matrix shows strong interconnection between ventilation, thermal mass, window to wall ratio, and shading strategies. So one important finding is passive design strategies do not work independently. Their effectiveness depends on synergistic interaction. For example, ventilation performance depends on the layout, shading effectiveness depends on the orientation, and thermal comfort depends on both envelope and airflow behavior. Therefore, the proposed passive design rating system framework evaluates passive designs multidimensionally rather than through isolated variables. So coming to the next slide, which is final passive design rating system framework that is being developed. So this slide presents the final structure of passive design rating system that was being developed. The framework includes 5 major criteria which were being discussed in the very starting at the Delphi technique, which is building layout and geometry, fenestrations, wall, roofs, and infiltration and air tightness. And from each of the parameter, sub criteria were being identified. So total 21 measurable sub criteria were being included. So in the screen, we can see for every parameter, some 5 to 6 sub criteria were being there, and what is the unit and indicator for each sub criteria is also being given in this one. And from this 21 measurable sub criteria and quantified benchmarking ranges were also being given. So each parameter was assigned weights based on literature evidence, expert consensus, and statistical validation. The framework emphasizes climate responsiveness, thermal comfort, and practical applicability. Unlike conventional systems, this passive design rating system framework specially rewards ventilation efficiency, moisture control, and climate adaptive design strategies. So coming to the next one, which is the certification parameters. So these are the total certification parameters that were being derived from the entire study. This slide presents measurable certification benchmarks. Each parameter includes quantitative thresholds, measurable ranges, and evaluation criteria. For example, we can take window to wall ratio. So, or we can take solar reflective index or air changes per hour values or thermal transmittance and shading dimensions. So for each of it, what are the sub parameters and what are the possible input parameters that we need to give it to this particular tool for quantification is also being given in this one. So we can see the quantifiable variations that we have it for each of the possible input parameters that we need to give. So these are all measurable and technically verifiable. So this transforms passive design assessments from a subjective evaluation into a scientifically measurable framework. And the proposed system can therefore support future building regulations, climate responsive certification, and sustainable residential policy development. So we can see the key takeaways. The certification parameters cover all the crucial passive design aspects from site orientation to air tightness and material performance. So we can see both the input values which are quantifiable, that is measurable values that we need to give as per different categories that we have it. And this passive design rating system uses these expert rated importance, feasibility, and suitability, and weighted using PCA derived components and aggregated into final passive design rating system that scores for certification that we have it. So coming to the next one, which is, excuse me, conclusions and key contributions. So in the conclusion, the research successfully develops a climate specific passive design benchmarking framework for warm and humid climates. The major contributions include the first climate specific passive design rating system for residential warm and humid residential buildings, and identification of measurable passive indicators, integration of expert consensus, statistical validation, and development of multi-dimensional rating framework. So the study also demonstrates that ventilation, shading, reflective surfaces, and adaptive comfort are most important in warm and humid climates than excessive insulation. The framework offers strong potential for sustainable housing policy, passive building certification, and future climate responsive building codes. So here we can see the summary of different findings. It's a first ever developed validated passive design rating system specifically for warm and humid climate ranges with the Kendall value and Chronobok alpha, which are being derived from the study, and two principal component analysis are also being explains 85.23% of variance, and 21 quantifiable parameters with weightages are being given, and ANOVA confirms core professional agreement on fundamental walls, expected divergence on statistical choices. So these are the key takeaways for practitioners and for policymakers. So for practitioners in warm and humid climates, prioritizes cross ventilation, shading, and reflective envelopes over insulation and air tightness. Coming to the key takeaways for policymakers, existing green building codes needs climate responsive calibration. Passive design rating system provides a replicable evidence-based model for updating residential building energy codes in tropical regions. So this is the glance of PDRS. So 21 quantifiable parameters, two principal component analysis, 85.23 variance, and 0.952, which is a Chronobok alpha value, and 25 experts were being involved from this one. So coming to the references, these are some of the key references and scientific studies that supported the research development, literature review, methodology, and statistical validation. So finally, thank you for your time and attention. I sincerely thank the conference organizers, reviewers, and my research guides for their support. And I look forward for your valuable questions and suggestions. Thank you. Thank you one and all for giving me this opportunity. I also thank OIDA, Ontario International Development Agency, for giving us this valuable opportunity to present the research among all of you. Thank you everyone. Have a good day.